Perfect. And with this beautiful intro, I will welcome everyone to our critical design review. Excuse me for the delay. Thank you all for coming. Of course, we're pretty excited about this. Thank you to all the members of the review board that are online with us. And I'm Fisnik. I'm a systems engineer and project lead together with Tobias and Sandra. And today we are going to walk you through our system, through our rocket, and we'll hope to get some great feedback from you guys. Also we're happy about all the questions that come in. First of all, before we start, I want to lose one or two words about Aquila. Some of you are for the first time here, so they weren't there when we had our preliminary design review. So I really want to say some quick words about Aquila. Why is Aquila so special for us? Aquila will be the first supersonic rocket of Space Team Aachen. So that's pretty huge for us. Furthermore, it's going to be the first Space Team Aachen rocket to reach 9 kilometers, so that's also very huge. And also, it's going to be the first German team to participate at the Spaceport America Cup. This is a major milestone, and today we want to have our critical design review. Last time we had our preliminary design review, where we went over our preliminary design, of course, and today we want to get more into what we did in the last few months about testing and refining our constructions and designs. So let's go into a little short overview. What are we going to talk about today? We start with a brief introduction, some team organization, finances, timeline, and so on. Then we're going to go into the system data, so flight trajectory, ascent data, descent data, all of this stuff. Then we are going to go into the system architecture, so how did we actually design the different parts in our system? And then, that's the most interesting part, validation and test campaign. What did we do? What are we still planning to do in the next months to validate our systems as much as possible? So let's go into the introduction. This is us. This is our team, at least part of them, not everyone's on there because we got some new members, it's a little bit old photo. And we are currently consisting of 5 different departments. So we have the mentors. The mentors are 3 people that already participated in Europe 2020 and 2021 and support us with their knowledge and their and some inside information that we need to for the designs. Then there's us, Tobias, Sandra, and me. We do the systems engineering and team leads. We keep track of the interfaces in our system, and as well as that the timelines are correct and all the deadlines are met, so these kinds of things. Then, of course, the backbone of every rocketry, we have simulations. Simulations will predict our flight data, our trajectory path, and they are consisting of 3 people. Then we have structures, of course. For the aerostructure, we need to have a team, and we have 5 of them who make body tubes, nose cones, bow tails, and so on and so on. Then we have our recovery system. We want to get our rocket back, and that's why we need a recovery system. For that, we have 4 people currently, and finally, we of course have our avionics team that tracks all the data during the flight and also keeps track of our telemetry so we can find the rocket after it has safely landed. So let's go on with our timeline. We actually started our project in November 2021, and we had quite a little hiccup in April when we wanted to participate at the EUROC, but couldn't. It was a little bit of a hiccup because we then decided, hey, what if we take more time and we just have a better rocket that we can then launch in America as the first team ever, first German team ever to participate at the Spaceport America Cup. So then we had an internal PDR where we presented our design to space team members. Then we had an external PDR where some of you already were in October. After that, we had the SAC application where we managed to be part of the 150 teams that participate there. And now we're here at the CDR. Hopefully the feedback and the insights from the review board will not be too big so that we can freeze the design end of January and go into the production and assembly phase. We want to cut that pretty short. We want to have a final rocket in April so we can have afterwards a test flight from the 20th to the 30th of April. After that, we will have a rollout event where we present our design to our sponsors, to our supporters, and everyone who wants to come. And finally, of course, in June, we will have the Spaceport America Cup in 2023. If we manage to get the rocket home safe and sound, we still want to participate at the European Rocketry Challenge 2023 and yeah, try to do what we already wanted to do last year. Let's get into finances and sponsoring. Just a quick words about that. The blue things are traveling costs, the red things are costs that we need to build the rocket on the left side. On the right side, that's our funds. And you can see that we kind of are missing 11,000 euros, but that's because we actually didn't account for sponsoring, for material sponsoring and machining sponsoring. So that's more or less covered. Then we also are covering part of the traveling costs by our personal money of the team members, because of course you can't bring everyone with the funds that we have to America. So we're also paying our own money, and we are still in the process of getting funds by searching for foundations and applying for funds. Here are our supporters and our sponsors. Quick shout out to all of them. Materials and machining is really what saved us and made us our rocket. So then I will give to Tobias.
Thank you, Fisnik. Also, hello from my side. First off, I want to thank you for attending the presentation, whether it's in person or by joining our online session. My name is Tobias. I'm one of the systems engineers of the project, and I want to talk with you about the key requirements that need to be fulfilled in order to participate at the Spaceport America Cup. I also want to give you a quick overview of our rocket design, and before we dive into our subsystems, I want to briefly show you the flight profile with a little animation. So for the requirements, we have the requirements divided in general requirements and in specific flight requirements. So you have to know, usually these kind of competitions are divided in two categories, the 3 and the 9 kilometer category. And the goal is not to fly as high as possible, but to reach a targeted height as precise as possible. Since the space team Aachen already flew 2 times in the 3 kilometer category with Car 1 and Car 2, as Fisnik mentioned, we now set a new goal to fly in the highest possible category at the Spaceport America Cup. So one of our general requirements is to fly to 9 kilometers with a commercial off-the-shelf solid motor. Additionally, we need to have a 4 kilogram functional payload, where at least 3 kilogram need to be the actual payload, and 1 kilogram could be, for example, a dummy mass. Furthermore, we need to have our recovery system successfully tested until the 1st of April. For the flight requirements, we need to have a stability between 1.5 and 6.0 calibers at launch rod clearance. So for everybody who doesn't exactly know what stability means, here's a quick definition. Stability means, or is, the distance between the center of gravity and the center of pressure measured in calibers. And the unit calibers refers to the diameter of the rocket. The center of gravity is the point around which the resultant torque due to gravity forces. What? Oh, thank you. Okay, I forgot to skip the slide. Okay, yes, center of gravity, the point around which the resultant torque due to gravity forces vanishes, and the center of pressure is the average location of where pressure is applied. So for example, when we have a stability of 1.5 calibers, then that means we have a distance of 1.5 times the rocket diameter in between these points. So when the motor starts to burn, the center of gravity starts to move upwards, and therefore the stability increases. When we move faster, the center of pressure moves down, and the stability therefore again increases. And when we reach the maximum velocity, or get to the maximum velocity, the center of pressure moves upwards again, and therefore the stability decreases. So you can see the stability is not fixed and varies during the flight. So why is it a problem when the stability is out of this range at launch rod clearance? So when we are over 6 calibers, the rocket is referred to being overstable and therefore more likely to move into the wind. So you don't really want that. When the stability is under 1.5 calibers, it is referred to being understable, and the rocket tends to turn, even could turn towards you. So that's normally something you want to prevent. We also need to have a dual event recovery system where our drogue parachute is ejected near the apogee. We need to have a descent speed of 23 to 46 meters per second with the drogue inflated. And our main ejection shall happen below 457 meters. With the main ejected or inflated, we need to have a descent speed of below 9 meters per second. So next I want to talk about our general design. That's how the rocket will look like. We will have a length of approximately 3.4 meters and a diameter of 11.4 centimeters. Our wet mass will be around 32 kilograms, so that's with the propellant, and when the propellant is burned, we will have a dry mass of 21 kilograms. So first start with the nose cone. The nose cone consists of the nose cone tip and the nose cone body itself. The tip is made of aluminum and functions as a heat absorber. Also, we have a heat and a pressure sensor located inside. Then we also have the tower located inside our nose cone and our avionics tower, and part of the ejection system of our recovery system, the CO2 tanks are also located there. When we go further down, we have the recovery bay, and we also have the nose cone bulkhead. So what is a bulkhead? A bulkhead basically connects and separates the different sections of the rocket and therefore allow an easy access of each section. The convention we have is that we call the bulkhead below the nose cone bulkhead, and for example, the bulkhead below the recovery bay, the recovery bulkhead. So every time we talk about bulkheads, you hopefully know now which one we are referring to. Inside the recovery bay, we also have our parachutes located, and below the recovery bulkhead and our payload section. For the payload, we will have a CO2 experiment where we basically suck in air during the flight and measure the CO2 concentration. Below we have the payload bulkhead where we have one of our launch lugs. The launch lug is basically there to guide the rocket during the liftoff at launch rail. Below that, we have the motor section where we have our solid motor, the fins attached to the motor section tube, and the motor bulkhead where we have our second launch lug. Then we have the bow tail, and the bow tail is there to reduce the drag during the flight and to hold the weight of the rocket. So here you can see a full cross-sectional view of our rocket. And before I will go to the flight profile, I will just mention some stats about our motor. We will have a Cicerone N3301 motor with 19.3 kilonewton seconds total impulse and a peak thrust of 5 kilonewtons. We will therefore, with that motor, have a maximum velocity of 1.68 and will slightly overshoot with 9.3 kilometers. Our maximum acceleration will be 15 g, and we will have overall stability during the whole flight of 2.9 to 6.4 calibers. So, as promised, we have a nice little animation for our flight profile. So what can you see here? We have the rocket, our rocket Aquila on the launch rail, and you have the time, the event, the corresponding total velocity, altitude, and stability. The first event will be the liftoff, where we will have 2.9 calibers and therefore meet the required 1.5 to 6.0 calibers at launch rod clearance. After that point, we reach maximum velocity at an altitude of 1,700 meters. And afterwards, we will have the motor burnout. After 10.4 seconds, we reach maximum stability, which with the mentioned 6.5 calibers. And we will reach apogee after 41 seconds. 1 second later, we will deploy the drogue parachute. With the drogue deployed, we will have a velocity of 24 meters per second. And afterwards, with the main deployed, we will have 8 meters per second, and then touchdown after 369 seconds. Okay, that's it for my part. I want to now hand over to Johan. Thank you very much.
All right. Thank you very much, Toby. My name is Juan. Hello, everyone. I'm the lead of the simulation sub-team for the rocket Aquila. I'll be presenting to you the system data. Thank you for attending. Thank you to everyone who is online. First of all, we're going to go to the simulation models and programs used in analyzing the rocket. Then we'll go to the flight profile, flight parameters. We'll go to the force profile as well. And we're going to take into account the wind influence. We're going to do a software comparison, which was the target of the simulations team. We're going to go over our CFD results, and then we're going to finish with the timeline for the simulation sub-team. So first of all, the simulation sub-team was focused on analyzing the performance and behavior of the rocket. What was important was that this is our first supersonic project, so it was a challenge for us to determine a methodology of simulating our supersonic rockets. And this was our task, so to say, to develop and establish a methodology for the space team to use for its future program, for its future projects, which include supersonic rockets. Okay, first of all, we're going to go through the simulations, models, and programs used. For the trajectory, analysis, we used 3 programs: OpenRocket, RockSim, RAS-Aero2. Those are the respective models we built in there. We also did CFD analysis, computational fluid dynamics. For that, we needed CAD geometry, which we also implemented. So all of these models, which you can see on the slide, are simplified models of the real rocket. The data is taken from the CAD model, that's structures and recovery designed, and we divided it into subsystems. We achieved their placement. Here you can see the parachutes, the recovery bay. This is the recovery hardware, and every subsystem has its place, its center of gravity, and with that we want to account for about like maximum 5% difference from real data with our flight predictions. So yeah, after that we're going to dive directly into the rocket analysis. We're going to begin with the total motion of the rocket. As you can see, the light blue curve is the acceleration curve, the red curve is the velocity curve, and the blue line, the dark blue line, is the altitude of the rocket. First of all, we begin with the total acceleration. We accelerate according to the thrust of the motor, and with that our velocity increases. After about 2.8 seconds, the vehicle becomes supersonic. We go above Mach 1. After that, we achieve our maximum velocity of 568 meters per second, which is about Mach 1.68. This occurs shortly before motor burnout, where you can see the acceleration is 0. Then this acceleration is the absolute value. It is actually negative, so the curve goes like this. The actual acceleration slows us down because we have drag on the rocket, and we go to the coasting phase. The coasting phase slowly brings us to our apogee of 9,258 meters. Our large acceleration points are the peak thrust, which is achieved at the very beginning. Sorry. Yes. So the large acceleration points are at the very beginning with the peak thrust of 14.5 G, and the main parachute deployment, which occurs right here after, not right here, but at the end of the flight. Yes, with 11.9 Gs. Okay. Next on, we're going to talk about the stability. This is also a very important parameter for us to analyze, as the rocket shall not be under or over stable at any flight stage. Toby talked about the stability a little bit. So you can see here the actual plots. First of all, the green curve you can see is the center of gravity, which Toby explained. It moves forward as the fuel burns out. We have the center of pressure, which starts at some point, then moves backwards as we pick up velocity. Then when we go supersonic, it goes down. The center of pressure moves further ahead, which lowers the stability. After that, we go back to subsonic speeds, and it goes back up. And after that, it goes slightly down. As you can see, the red curve is the stability margin calibers. It shouldn't be below 1.5, which it isn't at any point in flight, and at the beginning it is not dangerously high above 6. So we are safe. After that, the drag coefficients. We did a CFD analysis, so we're presenting the CFD results of the drag coefficients. Aquila is a pretty slim rocket. That's why the drag coefficients are also pretty low range, between 0.3 and 0.5. The drag coefficient begins at a value, then decreases slightly. After that, in the transonic region, we achieve about here the drag divergence Mach, which is about 0.9 for our rocket, and the drag coefficient raises dramatically. Still not too big of a value, it's 0.52. After that, in the supersonic region, it drops down again. About the force profile, it is also analyzed through all of those programs. The thrust is our generates the maximum force on the rocket. At the very beginning, this peak here you can see is the maximum thrust. Don't get confused, this red value is plotted on the right side, and this is the drag. It is of a much lower magnitude than the thrust itself. So the thrust is 5 kilonewtons, its maximum, and it is achieved at the very beginning of the flight. Then we pick up speed, we go, our drag increases, and our drag at max Q, that means maximum aerodynamic loads, is about 750 newtons. The other main load on the rocket will be the main parachute deployment. It leads to a large deceleration, and it is about 2 kilonewtons. And then we're going to land the rocket with the main and drogue chutes deployed, and we're going to land it with about 8.1 meters per second, which with our dry mass corresponds to a kinetic energy at landing at about 725 joules. All right, this was the flight profile and the force profile. We're going to take a look at the wind influence. We also analyzed the winds to make sure that the loads on the rocket are not too high of any cause vibrations, that the rocket is not overstable, and to look what happens at high wind speeds. The maximum wind speed allowed for launch is 8 meters per second at the ground level. From this wind velocity, I'm showing you here only the worst case. We built a wind profile which increases with altitude, of course, and we can observe the vibration, the oscillations which occur due to these winds. The critical region is about here. Here the velocities are high. Here they are supersonic, and of course any small angle of attack could lead to very high forces. So as you can see, this is the angle of attack, the absolute angle of attack. Here we don't have any oscillations. The angle of attack is super small, and the corrections occur immediately. So we are not imposed to high loads. Here the amplitude of the oscillations gets bigger, but this is at really low speeds. Therefore, it is safe for the rocket, and we are not experiencing any huge loads. Another thing to notice is the vertical orientation, which changes with time. The red curve is the vertical orientation, and you can see if we were to be overstable, the curve would prematurely decline to 0 degrees, but this is not the case. The curve goes to 0 degrees after we slow down our speed enough and we are close to apogee, which is normal. All right. Then we're going to go to the software comparison. This was the most important part for the simulations team. We compared the 3 software. As you can see in the altitude data, All right. As you can see in the altitude data, there is almost no difference up to the middle of the flight. After that, here is a small difference, especially at apogee, of course, which is the end of our ascent phase. But those results lie within 300 meters of one another, which is not too significant, but it is a difference. As you can see, RAS Aero 2 is the most optimistic one, Open Rocket is in the middle, and RockSim gives the lowest result for the apogee. The differences here are not that big. I'm going to show you the more problematic plots in a second. The velocity and acceleration curves are also quite close. The thrust curves are of course the same, as we are using the same model everywhere. You can see here, those are our kind of bigger concerns. This is the drag coefficient plot, which you can see there are 2 options here and here for RockSim. This is RAS Aero 2, this is Open Rocket, and this is CFD. As you can see, the curves are similar to one another, but the magnitudes aren't. And of all, CFD gives the lowest values, therefore we expect if the CFD results are successfully validated and correct, that the rocket will go actually a bit higher than those programs predict. Not a whole lot, but a little bit. The other big difference is in the center of pressure and respectively in the stability. This is important for us because we need to dimension our fins and our aerodynamic surfaces in such manner that we are stable. And as you can see, OpenRocket could be misleading in this way. It says that the center of pressure is much further than the CFD analysis says. We were surprised that RAS Aero 2 and Roxium don't give any logical values. What I mean by that is that we expect that the center of pressure raises with speed, then drops as we go supersonic, and then it goes back up. Those two plots doesn't show it, but the CFD results show as our expectations are. But as you can see, the CFD results show that that the center of pressure is much further than OpenRocket predicts, and therefore the stability can reach some lows. Those lows are not lower than 1.5 caliber, so the rocket is absolutely stable, and it's verified also through the CFD analysis. We can also analyze the stability with OpenRocket, but we need to take all results with a grain of salt. And last but not least, we're going to take a look at the computational fluid dynamics. We did this in order to be able to evaluate our softwares that we want to compare, and we wanted to get a better overview over the mechanical loads, over the thermal loads, the flow topology of the rocket that we can expect. So we're going to have a brief look. This is the velocity profile, the Mach number profile to be precise, at Mach 1.1. As you can see, as expected, here's the first shock wave that meets the rocket. After this, on the length of the nose cone, there is an expansion wave. After that, you can see the boundary layer growing as the Reynolds number gets higher due to the length of the rocket. After that, we have another shock wave right before the fins and an expansion wave right here. What we can notice is that the expansion wave is slightly bent, which shows us that this is exactly the moment of the transition between the transonic and supersonic regions. This is exactly where all waves get completely attached. And you can see here is the wake. I'm going to show the same thing. This is the static pressure at max Q. So you can see here the angle is much higher, which corresponds to the higher Mach number we're having. Of course, the static pressure increases very highly at the nose cone. Then at the expansion wave, it drops. Then again at the other shock, and on the edges it is quite high. On the expansion wave is quite low, and here in the wake it gets a region where it's high, and then it gets normalized. With this, our system data chapter concludes. I want to talk briefly about the next steps of the simulation teams. We plan to validate the CFD methodology. We're going to do a mesh validation and code-to-code validation in collaboration with the DLR. Basically, the mesh validation is tested with different meshes so that we can determine if the mesh influences in any way the simulation results. And the code-to-code validation is to test the solver if it's predicting accurately what the flow topology and what the metrics are. After this, we're going to use the CFD results and integrate them into ASTOS. This is another trajectory simulation tool, and we're going to simulate the trajectory through ASTOS and compare it again with the other software. Then we're going to do Monte Carlo simulations. This is for the predictions of the landing site. After that, we're going to do a final simulation cycle with real-world data when the rocket is getting built. We're going to weigh each component, build even more precise models, and do a last simulation cycle. So, how we're going to distribute this in our timeline? We are here at the CDR. We are currently working on validation and ASTOS. Once we finish them, we're going to start with Monte Carlo simulations. Our plan is to get it all done until April. After that, when the rocket is built, we're going to take on the final simulations with the real-world data. So that's it from my side. Thank you all, and I'll give over to Yanis with the structures part.
All right. Hello. Thank you to everyone for coming. My name is Yannis. I'm the lead structural engineer of Aquila, and so today it's my pleasure to present the structures part of today's presentation. Firstly, I'll give you guys a little bit of an overview over the structural design of Aquila, and then I'll cover the updates and changes that have occurred ever since the PDR. Unfortunately, in the interest of time, I'll not be able to cover the whole design, but I'll try to give quick recaps whenever I can. And then lastly, I'll talk about the timeline that's remaining up until launch in June. Okay, this is the structural overview. Obviously, the amount of subsystems haven't changed ever since the PDR, but especially with the nose cone, the recovery and payload bulkheads, and the fins, significant changes have occurred since the PDR. I'll cover those coming in the later slides. This is a design overview. Since the PDR, not much has changed. Once again, I'll go through the details in the upcoming slides. Okay. Moving on to the nose cone, this is the nose cone. A couple things have changed with this. Firstly, we have once again completely redesigned the avionics tower. The 360-degree cameras have been removed from the nose cone design and have now moved down to the payload section, specifically to the recovery bulkhead. And moreover, we removed 3 cameras, but we also added 1 camera. We added an ejection cam to the lower part of the nose cone bulkhead. And I'm personally quite excited for this, as I think this will provide a cool coverage of the hopefully successful ejection. And then we did add some more boreholes to the nose cone bulkhead lid. And finally, we decided to increase the nose cone wall thickness from 1.8 to 2.4 millimeters. All right. This is the nose cone. We selected an aluminum alloy. Other than that, not much has changed. We are still a little bit uncertain of how we're actually going to manufacture these boreholes, as they are quite small, but have a high length. We are in discussions with the WZL, which is the Laboratory for Machine Tools and Production Engineering here in Aachen. We'll have a meeting about this next week, but well, because this is just an auxiliary system of Aquila and not part of the critical design, if this ends up not working out, this is not in detriment to the overall success of Aquila, so it's not a main priority for us. Okay, moving on to the avionics tower. This is the old design. And this is a new one. As you can see, we've managed to, in my opinion, make the whole design a lot more elegant. We've shrunken down the whole design. It's a lot easier to print. It now features mounting points for example, the CO2 tank. Yes, and as you can see, it does once again feature all the components and features that we need to host all of the avionics and recovery systems. Then the bulkhead, nothing much has changed for the nose cone bulkhead. We have selected an aluminum alloy, as you can see. And then finally, we did add some more boreholes to support additional functionality for the recovery team. These are manufactured components that we have already assembled. We have assembled and manufactured every component of the nose cone except for the nose cone tip. And I do want to point out that we have at least 2 of each component, so we're already redundant and have spare parts available for everything. Okay, so moving on to the body tubes. The body tubes, maybe I'll give a quick recap for those who haven't attended the PDR. We wrote an entire project thesis about where we compared different manufacturing techniques of how to produce carbon fiber reinforced engine tubes for rockets. And in that project thesis, we selected 2 different manufacturing techniques, which is first of all split molding and roll wrapping. And ever since we have concluded this project thesis back in September or beginning of October, this whole topic has been figured out, so no changes since the PDR in that regard. Now I'm going to talk a little bit about the recovery and the payload bulkhead. Some significant things have changed with those designs since the PDR. First of all, we did select an aluminum alloy. We set a length for the adhesive surface length of 50 millimeters, and we also selected a glue, which is the DP490 by 3M. We also selected an anchor point. We added, well, as I mentioned before, we moved the 3 cameras down from the nose cone to the recovery bulkhead, and we have added some recesses to actually find space to mount these cameras. And then lastly, the launch lug has moved from the recovery down to the payload bulkhead. Okay. Then the fourth and final bulkhead is the engine bulkhead. With this one, we've selected an aluminum alloy. Other than that, no design changes. And then moving on to the bow tail. The current idea of the bow tail has not changed, and we are planning on 3D printing the nose cone using PEEK and PA reinforced with carbon fiber. But we are currently in the process of writing a bachelor's thesis about how to implement a crush core design into the bow tail. And in that case, we would use a metal 3D printer to manufacture the bow tail. However, as the bachelor thesis has not progressed far enough, we're still, the decision of which one to go for is still pending the results of said bachelor thesis. But even if it turns out that it's not feasible to add a crush core, we can always go back to the current design. So this does not present any significant risk for Aquila. And now to the fins. The fins have progressed quite a lot in the past couple of months. We have selected an epoxy, and we also selected a glue. And we updated the fin shape. We moved from a trapezoidal shape to now using a clip delta shape. And this made it necessary for us to redesign the mounting rig of the fins. We've concluded doing that, and we have also, as you can see in the 2 pictures, manufactured our first fully working fin cans. And then finally, with regards to the structural updates, we've got the launch lugs. As I mentioned before, the upper launch lug has moved from the recovery to the payload bulkhead. And other than that, once again, there hasn't been any significant changes since the PDR. This concludes the structural updates. Now, in regards to our timeline, we just 1 or 2 weeks ago, we just concluded our test campaign and validation phase, and we're quite happy with how that turned out. I'll be back here later on to talk a little bit about that. But for now, well, today we've got the CDR, and obviously we're waiting for your feedback. But after that, we are hoping to freeze the design of the structural components of Aquila, and then we'll move on to actually manufacturing and assembling the first instance of the Aquila rocket. Up until roughly the middle of April, we have quite a solid plan lined up to make that work. So we're ready just in time for the test launch that will take place at the end of April. And after that, in May, we'll work on producing spare parts. Our aim is to have full redundancy and have at least one spare part component available for every part of the rocket. And then finally, we will also work on launch readiness, meaning we will review our checklists, we will practice the assembly and all that beautiful stuff. And then finally, we'll have the rollout event at the end of May. And then excitedly, we will have the launch of the Aquila rocket at the SAC in June. Thank you very much. Like I said, I'll be back in a bit to talk about the validation, but for now I'll leave the mic to Florian, who's the lead of the recovery team. Thank you very much, and yes, see you later.
Hello, my name is Florian, and I'm the lead engineer of the recovery team, and I will talk about the recovery system. This is an overview of the recovery system. From the bottom to the top, you can see the main rocket, the nose cone, the main parachute bag, the main parachute, and the drogue chute. Everything is connected via short lines and shock cords. The whole system is going to be packed inside the parachute bay with the nose cone bulkhead on the top and the recovery bulkhead at the bottom. On the right side, you can see a CAD model from the rocket, and on the left side, you can see the components all packed tightly inside the nose cone. Of course, the shock cords, we need the shock cords to connect every part to each other. The shock cords are manufactured here at the RWTH Aachen at the Institute of Textile Technology. We will use a 24 filament Dyneema rope, and it will be packed neatly inside the tube. On the top picture, you can see the shock cord bundled together to reduce the risk of entanglement, and on the bottom you can see the shock cord with an electrical wire attached so that we can trigger the main release mechanism. Of course, we need to protect the cords. So if the cords rub or have the chance to rub against something like a sharp edge from the carbon fiber tube, we apply a protection sleeve. This protection sleeve is going to be made out of Kevlar and is going to be tightly wrapped around the rope so that we lower the risk of damage during the descent. The main parachute is inside a Kevlar bag. The Kevlar bag is 1.5 meters long, so the canopy is stretched out, and when it's time to deploy the main parachute, it's already elongated and doesn't have the chance to entangle itself like it happened with the car rocket before. We selected a ripstop nylon for both canopies for the parachutes. The main parachute canopy diameter is 3 meters, and the canopy diameter for the drogue parachute is 0.9 meters. Ripstop nylon is commonly used in parachutes, and we use an elliptical shape for its simplicity and relatively high drag coefficient. We also did tests about that, but more on that later. How do we eject the drogue parachute? To eject the drogue parachute, we use a cold ejection system, so we eject the whole nose cone with the nose cone bulkhead. On the right, you can see the CO2 system. On the top, there's a tank, and on the bottom, there's the valve assembly. It doesn't have the need for any pyrotechnics and can be recharged. There's a closer look. You can see it consists of 2 identical valve assemblies. In this picture and in the other pictures, you can see it's only connected to 1 tank, but in the future we will probably change it to 2 tanks, so it's a fully redundant system. Each of the valve assemblies consists of a ball valve with an electric motor and a switch. When the electric motor gets its firing signal from the avionics, the ball valve turns, the switch activates and gives feedback to the avionics, and the CO2 rushes out of the tank into the recovery bay that pressurizes it and pops off the nose cone with the bulkhead that was previously held in with shear pins. So now, how do we fill the system? On the left side, you can see the EV1 and EV2 valves are the motorized valves that we use for the ejection. Then there's the main CO2 tank. The MV2 valve is the MV3 valve is the main fill valve. Then a quick connect and the assembly for filling. On the right side, there's a CO2 tank. On the picture, it's inverted, but it also can we also can use a bottle with a riser, so that we ensure we have liquid CO2 in the tank. The procedure is as follows. We open MV1 and MV3. First we connect everything, then we open MV1 and MV3, then fill the main tank with CO2 purged through the EV1 and EV2 valves, and close everything back up and vent through the MV2 valve. Now that we have the main the drogue parachute ejected, we need to deploy the main parachute. For that, we will use two different types of release mechanism. One is a tender descender. This style of tender descender was developed by a co-project of ours, the STAR project, and we will be flying one of those. You can see in the picture there are two redundant tender descenders, but we only use the top one, and the bottom one will be replaced with something else, and I'm going to talk about later. How does a tender descender function? It's a pyrotechnic charge that blows out a little bolt that releases the ring. You can see on the left side. So this part gets blown out and the ring gets released. The other release mechanism is called a decoupler. It's also self-developed. It uses a ball bearing locking mechanism. So you have an electric motor that turns a camshaft. When the camshaft is turned, the three balls can fall to the inside and the cap is released. Now let's talk about the whole sequence. As I mentioned before, the drogue parachute is deployed and pulled out by the ejection. Then it unwraps from its Kevlar blanket that protects it against the CO2 charge. The drogue parachute pulls out the rest of the system of the ropes and of the main bag. Then at roughly 450 meters, the avionics trigger the release mechanism and the main parachute inflates and it sinks to the bottom slowly and safely. Now to the timeline. So now we have the 19th of January with a CDR. After that we have to do a little bit of validation, and we have done some validation, but not all is concluded yet, but I will talk about that later. Then we will manufacture all the components that we need for a successful flight. Then we have the test flight at the 8th of April. Then we have a final validation phase in case something went wrong. We have to see what's the cause of it, change something. Hopefully everything goes to plan. And then we have a rollout event and the SAC later this year. Now I will go over to Johan from the avionics team.
Thank you very much. I'm Johan Schepke, the head of the avionics team of Aquila, and I'm gonna walk you through the electronics that we designed for our rocket. As the avionics team, we have two main mission goals, and the first mission goal is to trigger the parachutes, as already mentioned, in the right moment. And the second goal is to find the rocket after it's landed somewhere in the desert. So that means we need to send back a location of the rocket. We call that the telemetry. Furthermore, we implemented a few other systems. We call those the auxiliary systems. And on our self-developed hardware, there's running self-developed software. First of all, we're going to take a look at our recovery system. Our recovery system is split into two parts. The first part is commercial off the shelf. That means we have a flight computer that is fully able to deploy both parachutes in the right moment. and we have a second one which is able to do the same thing. The first one is commercial off the shelf. That means we buy it and install it inside the rocket. And the second one is a self-developed option, which I go into more detail now. Our self-developed flight computer is called Kaput. It offers a barometric pressure sensor and an inertial measurement unit. And these sensors interface with the ESP32 as the main processor. And as the output, we use a motor driver which controls our parachute events. Furthermore, we have an SD card and a flash chip on board to store the collected data during the flight and analyze the flight afterwards. That brings us to the board flight computer. We use the Altrosmetrum Telebega. It offers up to 6 outputs to control the parachutes and offers a GPS antenna and telemetry, so we are using the Telemega as our main telemetry computer. To ensure that none of the flight computers deploy the parachutes when we are not ready to deploy, that means when we are still on the ground, we are implementing an arming system. This arming system physically disconnects the flight computers from the ejection. That means we have switches which disconnect the wires coming from the flight computer and going to the ejection mechanism. When we are ready to lift off, we screw in a screw between those 2 switches and ensure that we are ready to fire the parachutes. Now we come to the power supply of both of our flight computers. We are using lithium polymer batteries, and we are using multiple batteries as we have a fully redundant system. For our Telemega, we are using a 1S 1000 mAh LiPo battery, which should give us around 11 hours of runtime, which is far more than we actually need. But if we have delays on the launch pad or struggle finding the rocket after it's landed, it's better to have more than we actually need. For our self-developed option, we went with a smaller battery, with a 3S 800 mAh battery, which should give us around 6 hours of runtime. But as our self-developed option is not necessary to recover the rocket after it's landed, this is more than enough. Furthermore, our batteries are protected by a battery management system. This is a commercial off-the-shelf battery management system, which allows us to protect our batteries and our flight computers from accidents. That was it for the recovery hardware and brings us to the telemetry. The telemetry, as already said, is based around the Telemega. The Telemega has the GPS antenna and a radio on board, which sends back the location to the ground. It does this by the means of a monopole antenna, which offers linear polarization and is located on the top of our avionics tower inside the nose cone. On the receiving end of our connection are 2 antennas. The first one is a Moxoon antenna, and the second one is a Yagi-Uda antenna. And we multiplex these 2 antennas together and interface them into the teledongle, which is the receiver for the Telemega. This teledongle is then connected to a laptop running the receiving software of Altrosmetrum and displaying the data that we need to recover the rocket. For the sake of redundancy, we implemented a second tracking option, a so-called LoRa beacon. This is a small device sending off a signal of its location, and the signal is going to be picked up by our ground station, which is a small off-the-shelf LoRa gateway, which is also connected to our laptop. As LoRa is a standardized protocol, we have the option to receive the signal from other sources. That means many teams in the SAC will use the LoRa protocol. So there's the option that one of their ground station picks up our signal, and there are commercial providers of LoRa networks which can also pick up our signal, and we can get our rocket from them. As those beacons offer a battery lifetime of around 2 years, we are able to find our rocket even if we are struggling to find it immediately. That was it for the mission relevant part, and brings us to the fun stuff, the auxiliary systems. For the auxiliary systems, we implemented a dynamic pressure sensor, a temperature sensor, and as already mentioned, a separation camera. First of all, we're going to take a look at the dynamic pressure sensor. A dynamic pressure sensor allows us to determine the actual airspeed of the rocket. We do that by taking a pressure measurement in line with the flow and one orthogonal to the flow. And by comparing these two measurements, we can derive the actual airspeed of the rocket in the subsonic regime. That brings us to the already mentioned separation cam. The separation cam is looking downwards into the recovery bucket, into the recovery tube where the parachutes are housed. That means at apogee, as soon as our nose cone is ejected, we should get a good view of the drogue deployment and later of the decoupler deploying the main parachute. Furthermore, we have an additional temperature sensor inside of the nose cone tip. This is going to help us validate our simulation models by recording the temperature in the tip of the nose cone and comparing it to our simulated results. All of these sensors record their data onto our main flight computer and will be analyzed after the flight and not be used for the actual flight itself. That was it for the hardware part of things, and brings us to the software that's running on our flight computers. Our software is based around a so-called state machine. The state machine offers simple conditions to move from one state to another and ensures that our events are following a certain order. Basically, it means that we can't deploy our apogee parachute before we lift it off. If we take a closer look at these conditions, for example, if we transition from coasting to descent, that means that's the point where we want to deploy our drogue parachute. We need to get a vertical velocity smaller than 0. To determine our vertical velocity, we need sensor data, and the sensor data in our case is mainly the inertial measurement unit and the pressure sensor. As you can see here, the inertial measurement unit records the data in its local reference frame. That means it records, for example, right now the y-axis is our vertical acceleration. But as soon as we lift off, the rocket starts to pitch downrange, which means our axes are swapping. When we are at apogee, our x-axis is our vertical acceleration. That means we can't just take one axis and integrate it to get our velocity, but we need to rotate our coordinate system. That means we need the actual angle of our rocket. We do that by integrating all of our gyroscopic rotational speed measurements and correcting them for drift. And afterwards, we rotate our acceleration measurements into a global reference frame. And from that, we can derive the speed of the rocket, the vertical speed of the rocket, and the height of the rocket by the means of a Kalman filter. A Kalman filter offers the option to reduce the sensor noise and fuse two sensor sources together and output the things that you want. In our case, the height and the vertical velocity. That means we have finally the height and the vertical velocity and can trigger our simple conditions and therefore trigger our state machine one after another and determine successfully all events of our flight. That brings us to what's coming next. Currently, we are in the final phases of our hardware and software development. And after the CDR is finalized, we will go over into our testing and validation phase and simultaneously develop the payload electronics, which will be further explained by Lucas in a few seconds. After that, in the end of April, we will have our test flight. This will allow us to verify all of our systems and verify that our flight computer is working properly. And after the test flight, we will also go into a final validation phase, which will be focused on ensuring that our flight computer can't trigger in the transonic regime and working out all the final kinks of our system. And after our rollout event, we will ship off the rocket to America and we will launch and land successfully there. Thank you very much. I will give over to Lucas for the payload.
Thank you very much, Johan. Hello, everyone, and good evening. My name is Lucas, and I am responsible for the payload of our rocket Aquila. At first, I want to go over our requirements for the payload, give you an overview of our experiment and what we are trying to do with the payload, then how we designed this experiment, and also talk a little bit about the cameras and the electronics supporting the whole payload. Okay, the requirements are mainly set by the Spaceport America Cup. So we have to hit a certain weight target of 4 kilograms in total, where only 1 kilogram is allowed to be a dummy weight. So we have to be, the airframe for our payload has to be at least 3 kilograms, including all sensors and electronics and batteries and so on. Also, the payload has to be fully removable, so SAC personnel can actually weigh the payload before liftoff and verify our weight. Also, it has to be a passive system, so it has to be fully replaceable by a dummy weight of an equivalent mass without without changing any flight parameters or interfering in any other systems. The goals of our experiment are to measure the CO2 concentration in the atmosphere continuously along our flight path, meaning we will collect 2 data points per second with our CO2 sensor. And the second goal is capturing a panorama video of our flight using 3 cameras that are placed in a ring, looking in every direction, covering a 360-degree view of our of the launch site. The design, as you can see here, is we'll go from the top. On the top, you see the here you see the which bulkhead is it? The recovery bulkhead, and the cameras are integrated into the recovery bulkhead, which is really cool because it's not necessary for us to cut into the into our carbon fiber tubes for the camera holes. And also the recovery bulkhead features the air intake, so that we can replenish the air inside of the payload continuously, which allows us to sample new air and not sample like one air sample over and over. Under that, we have the weight. It's just a dummy weight of 1 kilogram, the exact allowed dummy weight mass. Under that, we have the batteries. There are 2 batteries which will make sure that our payload will function for hours, and does not make it necessary to load on the launch pad or to charge our batteries on the launch pad. Under that, there is a payload board which controls the whole payload system, and for most of all collects the CO2 data from the sensor and can control the fan and also the 360-degree cameras. On the bottom there is an air exhaust, allowing the air to exit from the payload. For the airflow, we are using a relatively standard PC fan that can move enough air to allow for to enable the airflow inside the payload. So the air will come in from the top and will be guided through a tube down to the fan and the CO2 sensor, and will the exhaust is in the bottom, as I already said. This reduces the actual volume of air that has to be moved, so we can use a less powerful fan because we have to move less air per second. Moving on to the cameras, we are using 3 RunCam Split 4 cameras. Those are the same cameras that are used in the auxiliary systems for our separation cam, and they are very small and should provide a very good video. They are evenly spaced with 120 degrees increments in the recovery bulkheads, and can be screwed in just before assembly. So assembly will hopefully be very easy. The payload board has some main features. So it is responsible for power delivery to the payload, to control the cameras, control the airflow, to manage communication and data collection, because we want to start up the fan and the cameras just before launch. So we have to communicate with the payload, and the payload board is doing that. And that was it for me, and I will give it back to Jannis for validation and test campaign.
Okay. Since the PDR, the validation and test campaign was the biggest thing that Structures has been working on, and so now I want to take you guys through that process. We utilized 3 different methods of validating our design. Firstly, we did FEM analyses, we also did material testing, and finally we did prototype testing. I'll start with the FEM analyses. Firstly, we did a bunch of static structural analyses of the nose cone, the recovery bulkhead, and the launch lugs. And then we also did a linear buckling failure analysis of the engine tube. And finally, we have not yet done this, but we will. It's planned. So upcoming is a drop test simulation of the bow tail crush core. And I talked about this before, but the crush core is part of a bachelor thesis that is up and coming. So those analyses will also be part of this bachelor thesis. Once again, in the interest of time, I'll not go through each and every one of the different analyses we did, but I do want to talk a little bit about the buckling failure analysis that we did. For this one, the engine tube is the one that's most interesting, as it's the longest tube and therefore most likely to fail due to buckling. The maximum load that we expect are 5 kilonewtons. And with those parameters, the predicted failure that would occur is predicted at over 160 kilonewtons, which results in a massive safety factor of over 30. And we were quite happy with this because this really high safety factor enabled us to decide that we were not going to do any hardware testing for the engine tube or for the tubes in general, as the safety factor is high enough for us. And this actually allowed us to save valuable resources and time within the last couple of months, which yeah, saved our sanity a little bit. And now moving on to the material tests, we did a test series where the goal was to find a high-performing and first of all reliable surface pre-treatment combination for the adhesive joints that we have in our system. The adhesive joints are how we connect the aluminum bulkheads to the carbon fiber tubes. And we did this in collaboration with the ISF, which is an institute that's focused on welding and joining here in Aachen. And we also did this in collaboration with STAR, which is the big brother of Aquila here in the space team. We tested 6 different combinations with 5 samples each, as you can see here in this table. And we selected a glue, which is the DP490 for these tests. And then finally, once we had manufactured and cured the 30 samples, we used a tensile test machine to test the samples. And these are the results. I'll not do a full analysis on the results right now. I would refer you to the CDR report. But in the end, we selected sandblasting for the aluminum and atmospheric pressure plasma for the carbon fiber. And with that, the biggest thing that we did is we did a whole test campaign, a whole prototype test campaign. And for these, we settled on using a shaker machine. You can see a video of how that works right here. Why did we use a shaker test? Because I think the first go-to would just be a normal tensile test. However, a shaker machine actually allows us to test our test articles a lot closer to the actual loads and conditions that we are expecting during launch. And so I think going from a normal tensile test up to shaker machine was a big step up in how close our tests are actually going to be to the real life conditions. We're doing this in collaboration with the SLR, which is an institute here in Aachen focusing on structural mechanics and lightweight design. And in total, we did 5 tests. Each and every one of them are full-scale tests, and we are using a mass simulator to add mass so that we actually can approximate the real loads that we are expecting. So in the end, with this test campaign, the goal was to validate the critical components of the structural design of Aquila in regards to the expected loads during flight. The first one was an adhesion test where we wanted to validate the strength of the adhesive connections between the bulkheads and the body tubes. So, as I already said, we used a shaker machine at the SLR for this purpose. And obviously, we used the selected pre-treatments that we selected in the material test series in the previous slide. The shaker applied an acceleration of 50 Gs, and this results in a calculated tensile force of 8.1 kilonewtons, which in turn, as our test article passed the test, validates our adhesive surfaces with a safety factor of at least 1.6. Here you can see a picture of what that test assembly looked like in real life, already mounted onto the shaker machine. Okay. Another critical component is the recovery bulkhead. With this test setup, we wanted to validate the strength of the recovery bulkhead for the forces that are going to occur during the main parachute deployment. We applied an acceleration of 25 G, and and in this case, this is a full-scale prototype, but we simplified the design a little bit to make the manufacturing process easier. For example, we did not manufacture the recesses where the covers would fit and get mounted onto the bulkhead. However, as this does not really affect the structural integrity and strength of the component, we just we simplified the prototype to make the manufacturing easier. And the test resulted in a test in a force of 4 kilonewtons, which validates the design for a safety factor of 2. Here you can see a picture and also take note of those sensors. Those are accelerometers that we added to confirm the acceleration that the test article actually experienced during the tests. Okay, this one is a variation on the first one, but this time we are, firstly we added the anchor point so that we also validate the anchor point and not just the recovery bulkhead. And secondly, we designed the test in a way so that the force insertion is at an 8-degree angle. Why 8 degrees? Well, the recovery tube extends up above the anchor point, and the recovery tube basically limits the maximum angle with which the parachute cords can pull on the anchor point. And this turns out to be 8 degrees in our case, which represents the worst case, and so we wanted to cover that scenario. Like I said, we included an anchor point in this one. We also added a load cell to confirm the loads that are, to actually confirm the loads that would occur during the tests. And we did this in this case because we actually had the space to add them right about here. The shaker applied an acceleration of roughly 16 Gs, which resulted in a, this time measured and confirmed tensile force of 5.5 kilonewton, which in turn validated our test article for a safety factor of 2.75. And then here you can see a video of what that looked like, and focus on this and those areas, as you can clearly see them lifting up during the test, which confirms to us that the entire load actually went through the anchor point and the load cell. Okay. And then lastly, another critical component is the entire nose cone assembly, as it houses the avionics. If something breaks during launch, it's a major, spells major problem for us. So we also wanted to verify that. In this test setup, we also included the avionics tower to test its structural integrity. And the shaker applied a force of 30 Gs, resulting in a force of roughly 700 newtons. And for this one, we also used frequency response functions to validate the structural integrity of the whole structure within different tests. And the whole assembly passed without any trouble, and we have therefore validated the design for a safety factor of 3. Which we're happy with, because for the nose cone, there's a lot more uncertainty when compared to, for example, the recovery bulkhead or the engine tube. So we aim for a higher safety factor to compensate for this uncertainty. And then finally, once again, a variation on the previous test. In this case, the worst possible angle that the parachute cords could pull on the nose cone is 90 degrees. So we wanted to test that. And also this time we once again included the anchor point. We pulled, the shaker pulled on the test article with an acceleration of 50 Gs, which results in a test force of 1.2 kilonewtons. I do want to point out that the accelerometer at the nose cone tip measured over 300 Gs, which is, in my opinion, really quite a lot, and speaks for the strength that our design has. And then finally, we used frequency response functions to validate the structural integrity. And the design passed without any trouble, and in this case we went a lot further and actually validated for a safety factor of 5. Once again, here's a quick slow-mo video of the test, and you can clearly see the whole nose cone bending. Okay, and with this test, we concluded our shaker test campaign, but we also tested the fins, as they are also quite hard to analyze using things like FEM, because for example the layup structure of the glass fiber is quite complicated, and so we wanted to make sure to validate the strength of the fins as well. In this first test, we wanted to validate for the planar forces that would be due to aerodynamic loads. And in this test, the trailing edge of the fins rests on this metal tube. We attached weights to the bottom of the fin can. Well, the weights are somewhere down here, but they attach right here. And then ratchets were used to slowly increase the load up until to a load of roughly 90 Newton per fin. We did not observe any defects, any cracking or any bending, and so the fins are validated with a safety factor of 2.5. And then last but not least, we also needed to check for the orthogonal forces that the fins would experience. Those forces are also due to aerodynamic loads, but also due to wind. For this, we fixed the fin can onto this rig, and then used a couple of acrylic plates that rested on 2 opposing fins, and then we added weights on top to go up to a load of roughly 950 newtons per fin. Once again, we did not observe any cracking, bending, deformations whatsoever, and so we are confident that the fins will be strong enough for launch, as we have validated the design for a safety factor of 3.8. And with that, we concluded the test campaign and validation phase of the structures team, and I'll once again give the stage to Florian. Thank you.
Hello. Now I'm going to talk about the test that we did for our recovery system. First off, we have an ejection test. This test was performed with the whole nose cone assembly, but only with one tank and one valve, as seen previously in the presentation. As you can see, the nose cone flew quite far. It had a velocity of roughly 12 meters per second when it exited the recovery bay tube, and this should be sufficient to pull out the rest of the recovery system from the tube. But further tests will be done to verify that, so we will put a parachute bag with the main parachute and a drogue parachute inside the bay and do another ejection test, or do another run of ejection tests to validate the to validate the deployment. We also tested our parachutes with the help of the STAR project. They built a test sled that can be attached to a winch that's normally used for glider planes or to launch glider planes. We pulled it with a velocity of around 60 kilometers per hour, and we had a test parachute with a diameter of 1.5 meters. We we measured the drag coefficient, and we determined a drag coefficient of 0.78 with a vent hole size of 14%. That's the most suitable for our application. We done this we attached the parachute to a load cell at the back of the sled and an anemometer on the top, so you can see the wind speed and you can see the drag, the force with which it pulls the parachute on the load cell, and so you can calculate the drag that the parachute has. We also did some traffic and some shock cord tests. You can see on the left side there is a table. The first three are the safety factors for the board components, and they're marked with an S because they're not tested by us. That's from the manufacturer. All the other safety factors where all the other measurements for the safety factor or for the calculation for the safety factors were done by us. So you can see the lowest is a 1.8, and this should be way sufficient. If you think about it, the safety factors are calculated for a speed of 100 meters per second at deployment for the drogue parachute, but we will probably not reach this high of a velocity at the drogue ejection. Unfortunately, we couldn't test the decoupler yet because we have some manufacturing delays, so this will be tested in the coming weeks, and hopefully this works. If not, we are going to use two 1080 senders as seen in the presentation before. We also will do a full scale system test, so everything put inside the nose cone and ejected, and then released, and then release the main parachute and see if everything functions correctly. Now I give over to the avionics with Johan.
Thank you very much. I'm going to walk you through the validation of our flight computers. And as already mentioned, we have two main mission goals. The first one is to deploy the parachutes, or trigger the deployment of the parachutes. And the second one is to find the rocket. First of all, we're going to take a look at the telemetry tests. For telemetry, we have already conducted a first range test of 1.5 kilometers and are planning to conduct further tests, further ground tests at first of up to 9 kilometers. And we also look into the option of testing the tracking system when the sender, in our case, the Telemega, is off the ground. There are different methods to achieve this, but currently we are looking at a few to verify our antennas without ground reflection. If we achieve 9 kilometers, that should be far more than we actually need, according to simulations of the landing site that we are expecting in the desert. These tests are going to be conducted as soon as our teledongle arrives. The teledongle, as already mentioned, is the receiver that we are using for the Telemega, and so we can do a full system test as soon as it arrives, we expect in early March. That brings us to our own flight computer, which mainly consists of ejection and recovery testing and also sensor validation. For our own flight computer, we have 3 different methods of validation. The first one is using simulated flights. We feed our flight computer simulated flight data and simulated sensor data, and it should determine when we have apogee and when we have main deployment and trigger these at the right time. The second validation method is using a small scale flight. As the physics are quite comparable to a large scale flight, we can use a small scale flight to verify our software and our sensors. And the last and biggest option is a full-scale rideshare mission with our flight computer in another rocket project that might be able to carry our own flight computer inside their rocket, and that way we could verify our whole system using the sensors and the algorithm to determine apogee. That's it from avionics, and I will go over to Fisnik to talk about our own test flight.
Thank you very much. Yes, let's talk about a test flight. That's the last part, and I would say it's probably the cherry on top of the ice cream of testing. Where can you actually launch a rocket in Germany? Well, here at Modellfluggruppe Quax. It's actually an association near Straubingen, that's near Munich, and they already participated in cooperations with, for example, the Technical University in Munich or the Technical University in Vienna, where they already made rocket launches. We talked to them and they gave their okay to make a test flight in late April. Where will it be? It will be in Straubingen, near Munich, and we will try to reach 1,500 meters of height. So it will be a small-scale flight. How can you achieve a small-scale flight with a rocket that's actually prone to go 9 kilometers? Well, let me show you something. We have this little bad boy, and this is actually the rocket motor of Carl 1, the rocket that flew in 2020 at the Euroc. This has significantly less impulse, so we will reach, with a little bit of extra dummy weight, a height of 1,500 meters. As I already said, the date will be in late April, so somewhere between the 20th and the 30th of April. And the main goal is, aside from obviously testing all of our systems in full integration, like the recovery system and avionics system, and giving them a full stamp of approval. Other than that, it will be a chance for us to test all the launch procedures and the concept of operations in a realistic scenario. So, what's next? We're coming to an end slowly, and what's next for us? You can see this beautiful building. This beautiful building is from the Spaceport America Cup, from the Spaceport America actually. And yeah, that's next. So we're going now into the assembly and production phase. Hopefully, our design will be frozen very soon, and then we can produce and assemble the whole rocket till April and go on this incredible journey with this incredible team. So, for us to have an incredible rocket, we need incredible insights of incredible experts. So, let's go into the feedback and questions round. Thank you very much. Before we go into the questions round, we are going to finish up with the YouTube live stream so we can have the questions round on Zoom. All right.